All right, so section 8.6 is the last section of material that's new that you're going to be required to handle or cover in chapter 8. You can skip section 8.7. The material that's in section 8.7, you do see if you take Math 218, the second semester of brief calculus. So it's not that the material's unimportant, so I want to skip it because of that. It's just because that in one section, I don't think I could do much more than confuse you about the topic. It's a topic called linear programming, and you spend about 3 or 4 weeks in Math 218 covering that topic. And in 1 hour or an hour and a half lecture, it's just, I can't get deep enough for you to even really appreciate the material, so we'll just skip that section. And in section 8.6, we're going to be doing two-dimensional graphs as opposed to number line graphs of inequalities. Meaning graphing on an XY plane. Probably at some point you did one-dimensional graphs on number lines. So what we previously, you may have done one-dimensional or number line graphs of inequalities. And that's going to be completely different than what we do today. But there's going to be a little similarity. So in red here, I'll just do a quick one-dimensional graph of an inequality. Like we might be asked to graph x is greater than 5 on a number line. So I might say graph x is greater than 5 on a number line. This would be considered a one-dimensional graph of an inequality. The reason it's an inequality because of that sign's an inequality sign. Inequality signs are greater than or equal to, less than or equal to. These are all considered inequality symbols. They're not equal signs. Equality symbols. I might as well write these down. This is greater than. This is greater than or equal to. This is less than. And the last one is less than or equal to. So this you may remember how to do. If you don't remember how to do it, it's not important to relearn it. But to graph x is greater than 5 on a number line, I'd probably create a number line, throw some numbers on it, at least get the number 5 on it somewheres. The number line to the far right edge goes off to positive infinity, off to the far left edge goes off to negative infinity. And to do a one-dimensional graph of x is greater than 5 on a number line, you're either, depending on how you learned it, going to put a round circle above the number 5 or a round parentheses above the 5 and have an arrow pointing off to the right. And this would signify every number on the number line that has an x coordinate bigger than 5. Any number to the left of 5, like 4, 3, 2, and 1, has x coordinates less than 5. Any number to the right of the open circle has an x coordinate bigger than 5. If I change that problem, said sketch a graph of x is greater than or equal to 5 on a number line, then the only thing I would do to change the graph is fill that open circle up with a solid circle. So that's one-dimensional graphs of inequalities on a number line. In section 8.6, we're going to be doing two-dimensional graphs of inequalities on xy axes. And it's going to be similar in that I'm going to have like a starting point and do a shading. In one dimensions, I either have an open circle or a closed circle for a starting point, and I either draw a line to the right or to the left of that starting point, depending on if it's a greater than or a less than. So it's going to be similar in what we do in this section, but instead of having a dot as my starting point and then shading a line off to the right or off to the left, I'm going to have a line as my starting point, and I'm going to shade a whole block to the right or a block to the left. Let me start with just the first couple problems. It'd be nice to have graph paper for these problems, but it's not absolutely required. Problem 1 wants me to sketch a two-dimensional graph of x is greater than or equal to 4, greater than 4, not or equal to. Problem 5 wants me to graph on a number line on a two-dimensional graph x is greater than 5. I'm going to do problem 2. I don't even know that I just said number 2. But to solve problem 2, I'm going to graph the inequality x is greater than 5 in multiple steps. First, I will graph the border, and the border is going to be the line x equal to 5. And I'm not going to have open and closed circles like I did with the inequalities. If the inequality has an or equal to, I get a closed circle. If the inequality didn't have an or equal to, I get an open circle. When I go to graph a two-dimensional representation of the inequality, if there is not an or equal to, I get a dashed line. If there's an or equal to, I get a solid line. So I will graph x equal to 5 with a dashed line. So each problem in this section, we're going to start off by drawing kind of the border. And to graph x equal to 5, equations that are drawn in two dimensions that only have an x will be a vertical line. So I'm going to find 5 on the x-axis, and I'm going to draw a vertical line. When an inequality or an equation in two dimensions only has an x, you get a vertical line that goes through the number that it's equal to on the x-axis. So this is a line of my border. Every point on this line has an x-coordinate of 5. None of them have an x-coordinate equal to 5, so they don't belong in my answer. But it's the boundary, because every point on one side of the line will have x-coordinates less than 5, and every point on the other side of the line has x-coordinates greater than 5. If I look at the numbers on the x-axis, any point to the left of my dashed line has an x-coordinate smaller than 5. So it won't be part of my solution. So there's no point over here that's part of my solution. Like, here's the point 2, 6. Its x-coordinate is 2, which is not greater than 5. Here's the point negative 8, negative 2. Its x-coordinate is negative 8, which is less than 5. It's not part of my solution. On the right-hand side of the line, every point has an x-coordinate bigger than 5. Like, here's the point 6, 1. Here's the point 9, 2. So to the right of my dashed line, every point has an x-coordinate larger than 5 or bigger than 5. And my goal in this problem is to, in a two-dimensional graph, identify every point whose x-coordinate is greater than but not equal to 5. And so every point to the right of this dashed line has an x-coordinate larger than 5. So somehow every point to the right of this dashed line is going to be included in my solution. And the way I graphically show that this is my solution is I shade all the way from the dashed line to the edge of my graph. What I'm doing is I'm covering up points, and every point that I cover, its x-coordinate is bigger than 5, so it belongs as part of my solution. And every point to the left of this line has x coordinates that are less than 5, and they don't belong in my solution. Sorry, I can't really shade so well. This is the complete answer for number 2. And as a general rule of thumb, if I'm asked to graph an inequality of the form x greater than some number, I do these steps. So to graph in 2 dimensions, as opposed to on a number line, so on an xy axis, which I mean in 2 dimensions, x greater than some number, we first draw a dashed vertical line through that number on the x-axis. And then shade every point to the right of that dashed line. So when you go to do problem 1, you're going to graph on a xy plane, x is greater than 4. You're going to draw a dashed line through 4, and then you're going to shade off to the right and cover up every point to the right of that line, because every point to the right of that line will have an x coordinate that's strictly bigger than 4. The next 2 problems are similar problems, except they have an or equal to. And I need to identify every point on the graph that has x coordinates that are either greater than -5 or equal to -5. I will first draw a solid as opposed to a dashed vertical line through -5 on the x-axis. And this will be a picture of every point that has an x coordinate equal to -5. This will show graphically every point that has an x coordinate equal to -5. So I'm going to draw a solid line, vertical line through -5 on the x-axis for problem 4. So I find -5 on the x-axis and I draw a vertical line. So each of the problems that we're going to do in this section, the first step is going to be to draw a line. And if it's a greater than or equal to or less than or equal to, I'm going to draw my line as a solid line because I want to include the points on the boundary. And if my inequality is a greater than or a less than, I'm going to draw a dashed line because I won't want to include the points on the boundary. So in this problem, I'm supposed to identify any point on this graph that has x coordinates that are greater than -5 or equal to -5. I've identified all the points that have x coordinates that are greater than -5, but I haven't, or equal to -5, but I haven't identified any points that have x coordinates greater than -5. When an equation only has an x greater than, you shade to the right, less than, you're going to shade to the left. So just like I graphed the last problem, I started off drawing a dashed line because I didn't have the or equal to, that I shaded every point to the right. I'm going to do something real similar in this one. To graph in 2 dimensions, x is greater than or equal to some number, I'm going to draw a solid line, vertical line, through whatever that number is. on the x-axis. So I'm really drawing a solid vertical line. And then I'm going to shade every point to the right. Because on the x-axis, numbers get bigger as you go to the right, and greater than means you want bigger numbers. So to finish up my problem, I need to shade. Every two-dimensional inequality graph is going to have shading on the entire one side of the line and no shading on the other. When you have x's for greater thans, are greater than or equal to, the side that you shade is the side that's to the right of the line, because on the x-axis, as you go to the right, the x-coordinates get bigger, and I'm trying to find every point on the graph who has an x-coordinate bigger than or equal to -5, and anything that I'm shading here in pink, all the way from the right at the edge of this line, but not touching it, well, right at the edge of this line over to the right, should be shaded. So this would be a picture of this inequality. The solid line shows every point that has an x-coordinate equal to -5, and the pink shading shows every point that has an x-coordinate bigger than -5. So when we have inequalities with x's and greater thans, if it's an x greater than but not equal to, you start off by drawing a dashed line through that number on the x-axis, and you shade to the right because of the numbers to the right of that dashed line are greater than the number that's indicated. If you have a greater than or equal to, you start off by drawing a solid line as opposed to a dashed line through that number on the x-axis, and you shade again to the right because numbers on the x-axis get bigger as you go to the right, they get greater as you go to the right. So you should be able to do problem 3 in 1. I'll move on to do number 6, and you might be able to do number 6 even without me. Number 6 is an x with a less than 6. I want to identify all the points in 2 dimensions that have x coordinates less than 6 but not equal to 6. So I need to graph the boundary. So I'm going to always, for all these problems, I'm going to start off by graphing a line. And in this case, I'm going to graph a dashed line as opposed to a solid line because I don't have the or equal to on the 6. So I'm going to draw a dashed line through 6 on the x-axis. The reason 6 is because x is less than 6. The reason dash because it's not equal to. And equations that only have x's graph to be vertical lines. So this would be a picture of x equal to 6, but I want only x coordinates that are less than 6, so I don't want to include that. And for x with less thans, because numbers get bigger as you go right and smaller as you go left, less than means I want to get smaller, I'm going to shade to the left. And I'm going to shade every point to the left of the line that I drew. My markers just don't really have much juice left this late into the semester, so let me do this. So I'm not doing the most beautiful graph in the world, but this is indicating that I'm shading every single point right up into that line, right up into that dashed line, and then to the left of that dashed line, because x's get smaller as you go to the left, and I'm told that I want x's that are less than 6, which are smaller than 6, which means I needed to go to the left. And made my graphs way too big, so I have way too much shading that I have to accomplish here. So my shading apparently is going to get progressively worse as I go through this section, but it is what it is. So to graph a line in 2 dimensions that has an x less than, first I'm going to draw a dashed vertical line through that number on the x-axis, and then I'm going to shade every point to the left of that dashed line. I don't know that I need to write that down, but I'm going to write it down anyways. So to graph x less than some number, we first draw a dashed vertical line through that number on the x-axis, and then second, we're going to shade every point to the left of that line, because on the x-axis, less than means smaller, and numbers get smaller as you go to the left. The next problems we're going to graph are x less than or equal to some number, and to do those, first I'm going to draw a solid line, vertical line through that number on the x-axis, and then second, I'm going to shade every point to the left of that line. Because less than means smaller, and on the x-axis numbers get smaller as you go to the left. So for x's, less thans are left, greater thans are right. Less thans without an or equal to is dashed. Greater than, less than with an or equal to is solid. Greater than without an or equal to is dashed. Greater than with an equal to is solid. So if I want to graph x is less than or equal to -1, I'm going to find -1 on the x-axis and draw a solid vertical line through it. That's all the points that have x coordinates that are equal to -1. And I'm going to finish up by shading every single point that's to the left of that line, because any point to the left of that line will have an x coordinate that is specifically less than -1, because x's get smaller as you move to the left, and less than means I want to shade smaller x's as opposed to bigger x's. And this is also done. Didn't really want to shade with these markers, but these markers will do monsterly quick shading. And I'm just going to live with that. I like the highlighter shading so much better, but my highlighters are kind of dead right now. I know I'm not going to finish this section this afternoon, so maybe I'll invest in some new highlighters. So you should be able to do 7. The next problems that we're going to worry about have only y's with inequalities, and when an inequality has only an x, you get a vertical line. When an inequality only has a y, you get a horizontal line. So to do problems 9 and 10, to graph all the points that have y coordinates that are greater than, but in my case not equal to 3, I'm going to start off, I'm going to draw a dashed but not solid, because I don't have the or equal to, horizontal line through 3 on the y-axis. So when equations only have x's, you get straight up and down lines. When equations only have y's, you get horizontal lines. And so I'm going to start off drawing all the points on the graph that have y coordinates equal to 3. Because my inequality doesn't have an or equal to, I don't put a solid line. And now I need to shade any point that has a y coordinate bigger than 3. And because y coordinates get bigger as you go higher, I'm going to shade up. And I'm going to shade every point above the line. And that's going to be the case for any y greater than problem. I'm going to start off drawing a horizontal line, and then I'm going to shade up. The reason I'm going to shade up is because every point that has a y coordinate bigger than a certain number is above it, because the y-axis gets higher as you, the point numbers on the y-axis get higher as you get higher. And so I'm going to shade every point above my line to get a really nice complete graph. So that would be a picture of y is greater than 3. So only x's vertical lines greater than right, less than left. Only y's horizontal lines greater than up, less than down. For number 12, to graph y is greater than or equal to negative 6, I'm going to draw first a solid horizontal line, through negative 6 on the y-axis. Easy enough to do. Find negative 6 on the y-axis, draw a solid line. It's a greater than, and because y's get bigger, and greater than implies bigger, y's get bigger as you go up, I'm going to shade every point above the line that I just drew. I don't know what I have left for drawing. I don't know if these will shade or not. Let me try this for my shading. Needless to say, my artistic ability is limited at best. And so I'm just shading every single point that's above the line that's on the graph that I made way too big to do all this shading. So when you're doing your homework, if you make your graphs a lot smaller, you have a lot less shading to do. But this would be a picture of every point that has a y-coordinate equal to negative 6, that's that solid line, and then every coordinate point that has a y-coordinate greater than negative 6, the shading. And that's perfectly what I want to do. So for y's, horizontal lines, or equal to's, solid, not or equal to, dashed, greater than you shade up because y's get bigger, and greater than implies bigger as you go up. Less than we're going to shade down because y's get smaller as we go down, and less than implies smaller. When I go to do 13 and 14, for 14 I'm going to start off with a dashed horizontal line, because I don't have their equal to, through negative 1 on the y-axis. So I'll start off with that. I'll find negative 1 on the y-axis, draw a dashed horizontal line, and it says I want y's that are less than, and because y's get smaller as I go down, I'm going to shade down as opposed to up. So for y's, greater thans you shade up, less thans you shade down. For x's, greater thans you shade right, less thans you shade left. So I'm technically not supposed to be going over that line. I definitely might wind up going over it a little bit, but it's okay if you do a little bit. So we'll get one more problem that only has a y, and then, or only has one letter, and then we'll start getting into problems with 2 letters, and they're quite a bit more difficult. For problem 16, it's tricky to get started. I need to find 0 on the y-axis, and 0 on the y-axis is going to actually be right along the x-axis. So to get started, drawing y is less than or equal to 0, number 16, I'm going to draw a solid line, solid, not dashed line, -2 if you make that dashed, a solid line, through 0 on the y-axis. And you can see 1's there, negative 1's there, 0 is right in between the 1's. And then I need to shade, and I'm going to shade down because I want y's that are less than 0. Less than 0 implies negative. For y onlys, less than is down, greater than is up. So I'm going to do my shading. Shouldn't really be crossing the line with my shading, but I would never take points off if your shading just barely flicks over the line every now and then. So for x-only lines and y-only lines, the shading is really pretty intuitive. For y's with greater thans are greater than or equal to, you're going to shade up. For x's with greater thans are greater thans or equal to, you're going to shade right. For y's with less thans are less than or equal to, you're going to shade down. And for x's with less thans are less than or equal to, you're going to shade left. And in general, if you get an or equal to, you get a solid. And if you don't have an or equal to, you get a dashed. That's about everything really succinctly abbreviated for what we did. So y's only are horizontal lines, greater thans are up, less thans are down. X onlys are vertical lines, greater thans are right, less thans are left. Or equal tos are solids, not or equal tos are dashed. The next problems are not fun at all and hard for students. Once you get them, you get them. It's kind of like learning factoring. Once you learn basic factoring, you can't figure out why you couldn't factor. So I'm going to start doing a picture with a dashed line of any point. If I add its x coordinate plus its y coordinate, I get a number less than 6, because this asks me to find every point that if you take its x coordinate and its y coordinate and add them, you get a number less than 6. I'm going to start off by making a dashed line of my border. A dashed line because I don't have an or equal to. And my dashed line needs to represent the border x plus y equal to 6. And in this section, the absolute best way to graph lines that have x's and y's is to find both the x and the y intercept. And what I'm going to do is I'm just going to make a table to get my graph started. I'm going to make an x column and a y column. And I'm going to start off putting a 0 in the x column and figuring out what y I get. If I put 0 in the x column, that tells me in my equation to go 0 plus y equal to 6. That's going to give me y equal to 6. That's going to be the first point I'm going to graph for this. It's the point 0,6. That point right there, the point 0,6, if you add up the x 0 plus the y 6, you get 6. Next thing I'm going to do is put a 0 in my y column, and that causes me to go to my equation and put a 0 in for y. I'm going to go x plus 0 equal to 6, and that's going to give me x equal to 6. Next I'm going to plot the point 6, 0, and now I'm going to connect those 2 points with a dashed line, and this will be a picture of x plus y equal to 6. It's the boundary of what I need to work with here. Every point on this line, if you add up the x coordinate and the y coordinate, they're physically going to equal 6. Like, here's the point 5, 1, and 5 plus 1 equal to 6. Here's the point 4, 2, 4 plus 2 equal to 6. Here's the point 3, 3, 3 plus 3 equal to 6. Every single point that's on this line has an x plus y equal to 6. No point on this line needs to be included in my answer because I only want points that have the x and the y coordinate when you add them, and you get less than 6. So I start off all these inequality graphings by making a line. And then after that, I need to know which side to shade. When you only have one letter, it's easy to know which side to shade. When you have two letters, it's not as easy to know which side to shade unless you're clever. So what I'm going to do is I'm going to pick two test points to help me figure out what side of the line I should shade. In all these problems, you're always going to shade one side of the line and the other side will be completely unshaded. And for me, I'm going to pick the 2 points that are as close to the x-intercepts that I can find. My test points are going to be the point 5, 0 and 7, 0. Reason I'm picking these is I can tell 5, 0 is on the bottom side of the line, 7, 0 is on the upper right hand side of the line. So I can tell what side of the line they're on. And what am I going to do with those points? Well, I'm very specifically going to take those 2 points and put them into the x plus y is less than 6 problem. The first point I picked was right to the left of the x-intercept. I'm going to plug in 5 for x and 0 for y and go 5 plus 0 is less than 6. This gives me 5 is less than 6. I'll tell myself that's true. 5 is less than 6. The next point I picked is 7, 0. 7 is x, 0 is y. I'm going to plug 7 for that x plus 0 for that y. So put 7 and 0 in for x and y. This is going to give me 7 is less than 6. And that's false because 7 is bigger than 6. So I'm actually done. I need to shade over the side of the line that has the true point. So I picked 2 test points on either side of the x-intercept, plugged both of them into the original problem and see if I get a true or a false. One side will be true, the other side will be false. Never will both sides be true or both sides be false. Now I need to shade, I'll say the true side. And 7, 0 when I plugged it in gave me a false answer, so that's the false side. 5, 0 when I plugged it in gave me a true, so that's the true side. When I go to shade this one, I'm going to shade right up to that line, but not crossing that line, and I'm going to shade everything, every point on the same side as that 5, 0. And there's a ridiculous amount of shading here because my graph is so big, so I would not make your graphs this big, and I'm going to get really kind of cruddy on my shading because it's going to take forever to do. So that's going to be a picture. Any point that I pick in the shaded area, if I add the x coordinate and the y coordinate, I'll get a number less than 6. Any point that I pick in the non-shaded area, if I add its x coordinate and y coordinate, I'll get a number bigger than 6. So when you go to do problem 17, you're going to start off like this. Plug 0 in for x and get a y. Plug 0 in for y, get an x. Plot those 2 points, which will be the point 8, 0 and 0, 0, 8 and 8, 0. And then pick 2 points on either side of the x-intercept. Plug them in to figure out which side of the line you're going to shade. All right, so problem 20. So first, for problem 20, I'm going to graph 4x plus 3y equals 12 with a dashed but not solid line. To graph this, I want to get the x-intercepts and the y-intercept. So I'm going to make an xy column. And the first thing I'm going to do is put a 0 in for x. So into that equation, I'm going to go 4 times 0 plus 3y equals to 12. That's going to be 0, so this is going to give me 3y equal to 12. And then I'll divide both sides by 3 and get y equal to 4. So that's going to give me the point 0, 4. I'm going to plot that on the x-axis. Then I'm going to put a 0 in the y column and put a 0 in for y and go 4x plus 3 times 0 equals to 12. That's going to simplify to 4x equal to 12 because the 0 piece will go away. I'm going to divide by 4, and this is going to give me x equal to 3. And that's going to give me the point 30. Now I'm going to draw a dashed line through those points the best I can. It doesn't have to be as nice as I'm doing, if this is even nice to you, I guess. But I get a dashed line as opposed to a solid line because I don't have the or equal to. Now I'm going to pick 2 test points. And I'm going to pick a test point on either side of the x-intercept. I'm going to pick this point right here, which is the point 2, 0, and this point right here, which is the point 4, 0. I like picking points on the x-axis next to the x-intercepts because it makes my work as easy as possible. And what am I going to do? I'm going to plug them right into the original 4x plus 3y is greater than 12. So my first point is the point 2, 0. I'm going to go as 4 times 2 plus 3 times 0. Is that greater than 12? Plugging in 2 for x and 0 for y. When I do that, I get 8 plus 0 is greater than 12. I get 8 is bigger than 12. Well, 8 isn't bigger than 12, so I'm going to write false here because 8 is not bigger than 12. And I'm going to write false by that 2, 0. Now I'm going to use the point 4, 0. So this was using the point 2, 0. Now I'm going to use the point 4, 0 and do the same thing. Plug in 4 for x and 0 for y and go 4 times 4 plus 3 times 0 is greater than 12. This is going to give me 16 plus 0 is greater than 12. This gives me 16 is bigger than 12. 16 is bigger than 12. I'm going to write true because 16 is bigger than 12. And next to the 4, 0, I'm going to write true. Now I'm ready to shade. I always shade the side of the line where the true point is. So the side of the line I'm going to shade is the true side of the line. And so I'm going to shade everything on my graph right up to the line and over the line and above the line. So you should be able to do the same for 19. The next 2 problems I'm going to do are going to be your problems because for whatever reason, when I wrote my answer key, I didn't write them right, and it's hard for me to correct PDF. So hopefully I get them fixed this summer. But for right now, I'm going to do problem 21 because currently the answer key is wrong. Hopefully by the time you actually go to check this, I get it fixed this summer. It's just I can't fix PDFs that easily. So let me graph first. So first, I'm going to graph x minus 3y equals to negative 6. And this one I'm going to do with a solid line because I have the or equal to. So how do I do that? I start plugging in 0. So into my x, I'm going to plug in 0 and get a y. So first I'm going to go 0 minus 3y equals minus 6. This is going to give me minus 3y equal to minus 6. And now I'm going to divide both sides by minus 3. And that's going to give me y equal to positive 2 because on both sides the double negatives turn positive. So I'm going to get the point 0, 2 as my first point. Now I'm going to plug a 0 in for y and get x minus 3 times 0 equals negative 6. And this is really nice. This just gives me x equals to negative 6. That's going to be the point negative 6, 0. So I'm going to go to the x-axis and put the point negative 6, 0 in. And I'm going to graph these with a solid line because of the or equal to. So I'm going to connect these 2 points, kind of the best I can. Certainly doesn't have to be perfect, but this is reasonable. Solid line because of the or equal to. Now I'm going to get my 2 test points. I always like to pick points on either side of that x-intercept. Here's the point negative 7, 0. Here's the point negative 5, 0. Apparently this checking's a little bit tricky because I messed up when I wrote the key. So how am I going to check? I'm going to use x minus 3y is less than or equal to negative 6. First, I'm going to plug negative 7 in for x and 0 for y. I'm going to go negative 7 minus 3 times 0 is less than or equal to negative 6. This is going to give me negative 7 is less than or equal to negative 6. That's true because numbers get smaller as you go to the left. So this point right here is going to be true. Negative 7 is less than negative 6. Now I'm going to work on that point. So this was with the point negative 7, 0. I got true. Now I'm going to work on the point negative 5, 0. Plug in negative 5 for x minus 3 times 0 is less than or equal to negative 6. The 0 piece goes away. This gives me negative 5 is less than or equal to negative 6. And negative 5 is to the right of negative 6, so it's bigger. It's not less than. So that's false. So a little bit harder when you're checking with negatives to tell if it's really bigger or smaller. To be smaller, you have to be further left. Negative 7 is to the left of negative 6, so it's smaller. Negative 5 is to the right of negative 6, so it's bigger. It's not smaller. And this is saying, is negative 7 is smaller than negative 6? True. Negative 5 is smaller than negative 6? False. I'm going to shade the true side of the line, which is up and away from the origin, is what I tried to write here. So I'm going to shade this side of the line. And this is what I mean, up and away from the origin. So there's the origin. I'm shading up as opposed to down. I'm shading away from the origin as opposed to towards the origin. All right, so that was a mistake that I fixed. Hopefully that worked okay for you. And for whatever reason, I just had a bad little flow. I messed up on 23. It'd be nice if you pause the video and try to do 23, but if you just not want to watch me do it, that's completely fine. You can take a second and just watch or do it. So if you're watching, let's go for it. So first, I'm going to graph 3x minus 4y equals to negative 24 with a solid line. So I'm going to plug in 0 for x first. When I plug in 0 for x, I go 3 times 0 minus 4y equals to minus 24. This gives me minus 4y equals to minus 24. And then I divide by minus 4, divide by minus 4. Both double negatives turn positive, and I get y equal to 6. The first point I'm going to plot is the point 0, 6. Now I'm going to plug 0 in for y and go 3x minus 4 times 0 equals to minus 24. The 0 piece goes away. This will give me 3x equals to minus 24. And then I divide by 3, and get x equal to negative 8. That's going to correspond to the point negative 8, 0, because I just plugged in 0 for y and got negative 8 for x. I'm going to plot those 2 points and graph them with a solid line because of the or equal to. Rulers are nice, but not necessary. It's nice if you throw arrows at the end of your lines, but absolutely not necessary. I think I've forgotten them every time. So what points am I going to check? I'm going to check negative 9, 0 and negative 7, 0. So let me try to check these somewheres. Let me check on another sheet of paper because I'm kind of running short on room here. So first point I'm going to check is negative 9, 0. And I'm going to check that in 3x minus 4y is greater than or equal to negative 24. So I'm going to go 3 times negative 9 minus 4y is greater than or equal to negative 24. With minus 4 times 0, putting in 0 for y, putting that 0 in for y. This piece is going to go away. This is going to give me negative 27 is greater than or equal to negative 24. And on a number line, it goes negative 24, negative 25, negative 26, negative 27. Negative 27 is to the left of negative 24, and To the left means it's smaller. So this is false right here because numbers on a number line as you go left are smaller. So this point gave me a false. Now let me work on the point -7, 0, plugging in -7 for x and 0 for y. This gives me -21 is greater than or equal to -24. And -21 compared to -24 is to the right. And on a number line, to the right is bigger. And this says -21 is bigger than -24 or equal to. Since it's to the right, it's bigger. -27, since it's to the left, is smaller. And I'm saying, is it bigger or not? -27 isn't bigger, it's to the left of it. -21 is bigger, it's to the right of it. So this is the true side for 23. And when I go to do my shading, I need to shade towards the true side, which is towards the origin here. So when I go to do my shading for 23, I'm going to shade over the true side and not shade the false side. So I'm shading everything that's beneath the line all the way to the ends of my graph. So I'll throw 24 up here, but I'm not going to do it, so I don't know that that's the best use of your time. But 24 and 23 are just like each other, so I didn't really feel the need to do both of these. So this is a good stopping point because we're a good hour into this video, or getting close to an hour. And then the rest of the sections are going to have a little bit different kind of a problem. And there are not that many problems left, but they take a little bit longer.